Hello everyone. As part of our course, MESC project course, ENGI 990, we are presenting our presentation, which was supervised by Dr. Ashraf Ali Khan, and the work was being done by Emmanuel Dala Kabwa, Emmanuel Kumsin, and James Baski. So as part of our presentation, we have the outline, and we will talk about introduction of the project topic, the motivation of this project, and we will compare HVDC and HVAC, and also talk about the literature review involved and HVDC topologies. And we will conclude and also talk about recommendations. Our topic is HVDC system for high energy storage system using St. John's, Newfoundland as a case study. So as I said earlier, our motivation for this project is we would emphasize on depleting fossil fuel. And it is actually projected that fossil fuels will be fully depleted by 2060 at the rate of usage. And this is a source from IEA. And also, one of the motivation is climate change concerns, which of course talk about green gas emissions, and also 75% of green gas emissions emanate from fossil fuels, warmer environmental temperatures worldwide, and also extinction of some special species due to climate changes. And also on our motivation agenda was growing renewable energy penetration into the grid. As we all know, the renewable energy is on the surge right now, and it's actually gradually taking over from fossil fuels. So we would go further and compare HVAC and HVDC systems by their mode of transmission. And HVAC make use of power transformers to step up voltage for transmission, whilst HVDC uses power electronics converters to boost voltage levels. We also took losses as a factor and compared, and we established that HVDCs has lower transmission losses compared to HVACs. We also took cost as a factor. For shorter transmission networks, HVACs has lower cost, and for longer transmission networks, HVDC becomes more cheaper. We also took environmental impact as a factor, where HVDC transmission networks require less corridor compared to HVAC. We connected it with the grid scenarios, and we talked about the interconnection of regional grids, where HVDC is more suitable for transmission links that interconnect several countries. For example, the North American and European HVDC interconnections. And another one is HVDC regional interconnectivity requires intermediary substations. What was it? Yeah.
Like what number? Slide number 6. And what's the time? So spend.
During our research into the HVDC systems for our project, we got to the realization that there are arrays of converters that we could use. Example is the LCC, which is a line commutated converters. Now, these are basically designed with thyristors and transistors, mainly switching devices. And we also have the voltage source converter, which is designed with MOSFETs and IGBTs. We know IGBTs, with time, we noticed that the IGBTs and MOSFETs were reliable switching devices as compared to transistors and thyristors. Now, moving on, we also categorized all these converters into two main broad categorization, that is the line commutated converters and voltage source converters. Now back on the converters. So with these two broad categorizations, we realized that the line commutated converters requires large inductors within the DC circuit to keep the current constant, whereas the VSC Thus, the voltage source converters do not require large inductors on the DC side because there is a direct control for the output voltage. Secondly, the other comparison between these two systems, the LCC depends on the circuits that are connected to be turned on. So in other words, the LCC requires a circuit to be turned on, whereas the VSCs are turned on independently. Then furthermore, the LCCs are more suitable for point-to-point HVDC transmission, whereas the voltage source converters are suitable for connecting multi-terminal transmission networks. For the high voltage DC system topology, we notice that there are several topologies available to us for this project. The first has to do with point-to-point HVDC. Now, this topology is suitable for high power transmission over long distance, and it composes of two converter stations interconnected by an HVDC transmission link. The second has to do with bipolar HVDC. Now, this topology consists of two point-to-point HVDC systems which are connected in parallel. Now, the configuration is suitable for a system that requires higher reliability and redundancy, as it enables point-to-point systems to remain in circuit while the others are maintained. The advantage of this bipolar HVDC is that the configuration allows for transfer of power in either directions. The next topology has to do with multi-terminal HVDC. Now, this involves interconnection between multiple converter stations, that's 3 or more, and they are normally through an HVDC transmission link. And the advantage of this is that it's suitable for interconnections of multiple AC grid or interconnections of several renewable sources. And our project is looking at connecting other renewable sources into a main grid, and we transmitting via DC. Then we also have back-to-back HVDC topology. Now, this topology involves the use of AC to DC converter to interconnect 2 or more unsynchronized AC systems. Now, usually, the converter station for various unsynchronized AC networks are situated close to each other.
Okay, so I can take it off from there.
So there are many options available for us for the design of our converter, but we opted for the isolated DC-DC converter topology. And the isolated DC-DC topologies simply means that the input side of the converter is isolated from the output side of the converter so it's achieved via galvanic isolation, that is by the use of a transformer, in this case a DC to DC transformer. So we actually used a dual active bridge circuit for the development of our circuit and then the simulation of our work. So we modeled our isolated DC-DC converter in Simulink, and the waveforms are presented in this presentation. And the circuit involves the rectification of a 3-phase 11 kV AC supply into DC. Now, a single module may not be able to handle the 11 kV AC supply. So what we did was that we built the dual active bridge and then kind of connected them together so that the input side is able to handle the 11 kV volts, and then the corresponding output was still maintained at 400 volts. So a single module was handling 1,100 volts, and then the output was 400 volts. So what we did was that we connected 10 modules of the
100 to 400 volts dual active bridge. And the configuration was that the input side was connected in series so that we can get the capability to handle 11,000 volts, and the output side, which we wanted to still maintain at 400 volts, was connected in parallel so that we can still maintain the 400 volts at the output. So then after we got the output, after we've gotten this configuration with the 10 modules connected together, we now used an inverter to also invert or convert the 400 volts DC to 110 volts AC, as will be seen. So this is the circuit for a single module of our network. So as you can see, we have the isolated DC-DC converter, we have your AC-DC rectifier, and then from there we come to the dual active bridge, and then from the dual active bridge we come to DC-AC inverter, which is with the end part of the circuit. But this is just for one. But in reality, our module is going to be taking 10 of the dual active bridges and connecting them. The inputs will be connected in series, and the outputs will be connected in parallel. So, as stated, a single dual active bridge circuit was first modeled in Simulink to take an input of 1,100 volts DC and produce an output of 400 volts DC. And 10 of these were later connected together. And then the resulting circuit has 11,000 volts. And then what we also did was that in order to maintain the circuit, or in order to get the circuit to give us the right distance, we phase shifted each of the DABs, the 10 DABs, by 36 degrees, so that it's like when one is on, the other one, that like the on-in time was phase shifted, so that they are not all coming on at the same time. So we use the 36 degrees phase shift for it. And then the simulation, after the simulation, this was the output waveform that we gotten at the input of the cascaded, or what do you call it, the multiple module DABs that we connected together. So we were getting our 11,000 volts DC at that output, as can be seen from the graph here. So this one, we just use the scope to connect to see whether after we've done our configuration, we're still getting the 11,000 volts that we were desiring. And then after going through the conversion to DC, which is 400 volt DC, we also connected the inverter, and the inverter was giving us this output here, which was equivalently, this is giving us our 110 volts root mean square value for our project. In conclusion, we will say that we were able to connect multiple modules of a dual active bridge circuit, and then by doing that, it was able to handle higher voltage, which means that if we want to even increase the voltage carrying capacity of the converter, all that we have to do is to continue to cascade it. And then the same way, if we want to increase the power carrying capacity too, is just a matter of adding them on so that we can continue to get so that the circuit can handle much higher power within a circuit. On this note, we bring our presentation to an end. Thank you.